see the presentation.
Okay, so good morning, everyone. Thank you. Sometimes when I'm talking to geeks, I thank you for waking up so early in the morning for the pleasure of listening to this. Because I mean, for geeks, this is indeed very early morning. This is just one slide about us because this is very little about us. But we as Raincode Labs, we are, that's called, what I call bragging rights. We are the biggest independent compiler company in the world, and by quite some margin. We are like 50, 60 people compared to our competitors who are essentially 2 people working in a garage. And we are a company specialized in anything that deals with programming languages. Compilers, interpreters, translators, IDEs, whatever. That's everything. Anything that deals with programming languages more than with natural languages is our domain. And we're based in Brussels, Belgium. We have a facility in Bangalore with 7 people right now. But we are still very much, I would say, Belgium-centric, as you can imagine. And we do have job openings and internships for those of you who may be interested. But this is not, let's say, this is not a presentation about Raincode as a company and why you should come and work for us. This is, we're going to be talking about something else. So let's move on. This is about YAFL. This is about YAFL. And before we proceed, I am going to start with a platitude. A platitude is a statement that is so freakingly obvious that no one should question it, that the opposite statement makes no sense at all. And the statement goes as follows. Software that matters lives for decades. Anything that has value, anything that really makes a difference in the world when it comes to software is software that's going to be living for years, for 10 years, for 20 years, for 30 years. Something that lives for a few months obviously will not matter that much. I think it's fairly straightforward point, and it's very an academic, because in academia the timeline goes, oh, you come up with an idea, you write some code to demonstrate it, you publish a paper, and 6 months down the road you move on. And the time span of your software is 6 months, which means that you have a very different sense of concern. We, in the world I live in, both for the software we write and the software we process for our customers, we're talking about totally different timelines. And there comes one of my favorite questions. As a matter of fact, we can use the chat. The problem is, can I see the chat here? Let me see if I can see the chat. I can see the chat. In the chat, could you please answer this question? If you were to write a piece of software, I'm not even sure I'll be able to see the chat though, but if you were to write a piece of software that has to live for 30 years, what programming language would you use? And you can do it orally. I mean, you can unmute yourself, promise there will be no repercussion. This is not an exam, but let's say from the top of your head, if you were to say, oh, I'm going to write a piece of software that's going to live for 30 years, what programming language would you consider? This is not a rhetorical question. This is a question.
Yeah, I would also use C or Java.
Okay, C or Java. Anything else?
Someone answered COBOL, Erlang, C++.
Okay,
yeah.
we can go through these. It's an interesting mix of answers, So Java. Well, if you were writing in pure Java, what I call pure Java is, well, you write Java classes of your own. Oh, that would probably work. But the problem was that when you write Java, you don't write in Java. You write in Java and you have hundreds of dependencies on libraries for which provided by different organizations with different timelines. Some are going to be released every 6 months and going to be incompatible with each other. People that have a serious Java footprint end up spending a significant amount of their time, 20, 30, 40%, doing nothing more than keeping up with the evolutions. For over 30 years, Java is a very annoying proposition, really. C is one of the possible answers, granted. Let me see. I see 3 possible answers really to this question. C is guaranteed to be available for the coming 20 or 30 years, easy. No matter what happens, no matter where computing goes, C will still be available. COBOL will also be available. Don't get me wrong, I'm not saying that C or COBOL are good languages. I think that they're both extremely bad languages in many, many different ways. But that's not the question. The question is, will there still be adequate C and COBOL compilers in 20 or 30 years? And yes, there will. For those of you who think that COBOL is a dead language, think again. Your life is controlled by COBOL. Your taxes are controlled by COBOL. Your bank is running on COBOL. COBOL is not going anywhere anytime soon. Again, as I said, this is not me telling you that COBOL is any good. There's no such thing as being proven by time in our industry. COBOL sucks big time, but it's going to be there. And then there's the last answer. So, well, one way for you to survive the evolutions in languages is to build your own. I really think it's interesting that in 2021 people say C++ because you know what? 20 years ago, C++ felt like a safe bet. Now, essentially, the market share of C++ has been squeezed between C on one end and Java on the other. And C++ is probably no longer a very, and it has its technical problem as well. I mean, let's not get into that. But as a future-proof solution, C++ is not guaranteed. So building your own is essentially saying, well, you know, instead of depending on someone else's willingness to maintain a language infrastructure for my software to be able to live longer, I'm going to maintain my own. And obviously, you could say I'm cheating because we're compiler people, so for us, it's easier. And that's absolutely true. It's easier for us to maintain our own language than it is for most organizations. But that's part of the rationale. And as the story goes, I mean, YAFL, which is the topic of the talk today, has been in use for 30 years, which doesn't make me feel any younger, as you can imagine. But YAFL is really our way to independence. YAFL is really the tool we use so that our software can live longer than it otherwise could. The truth is, this is not how it happened. I'd love to say that when, I mean, it's no secret, I started working on YAFL. I was 25 years old or something. I'd love to say that I had the brilliance of understanding what I was getting into and what the impact would be and that was a strategic move. That's absolutely not how it happened. This is the typical case of post-hoc rationalization. YAFL happened in a totally different way. It started with me being a very, very arrogant student, and I have to again apologize for that. And at that time, Ada, which some of you may even have heard of, was presented like the language that was supposed to, you know, clean the slate and say, well, from now on, everything will be written in Ada. And to put things mildly, I was not crazy about it. I'm still not crazy about it. I think that Ada in many ways is a very flawed design. And because I was a bit too arrogant, I was a bit too loud with my opinion until Raymond de Villers, who ended up being my PhD supervisor, who's a very sweet guy and very nice, ended up losing patience and said, you know, you're so smart, why don't you design a language? And that's essentially how it started. My master thesis was the design of a language, which I then called YAFL, and my master thesis was the documentation, the specification of the language, which is we refer to as the YAFL programming language release 1. And there were a couple of interesting basic ideas. A, it has to be different from Ada. We really thought that Ada was a very poor design. B, we wanted to conquer the world. In other words, I was still living with the delusion that, oh, by designing a better language, I'm going to have many people use my language. C, I really wanted the language to be easy to implement. Ada was typically a language that was designed with absolutely no concern for implementation in mind. And that ended up being a real issue. Implementing Ada is a big issue. And it's not the only one. I mean, for instance, that's one of the real issues with C++. C++ is such a complicated language that there are like a couple of truly conformant compilers out there. It's virtually impossible to get C++ right. So I really wanted a language that was easy to implement. And the idea was to go for abstraction over performance. Based on the assumption that we optimized way too early and that we I should focus on better abstraction rather than better performance. And that was a flaw of mine. I always was optimizing too early, and I really tried to fight this, and I haven't been all that successful, I have to say. So what can we say about YAFL? It's an object-oriented language with single inheritance. Remember, that thing is 30 years old. So people come to me and say, well, it was functional languages. Well, back then there were no functional language. Functional language were not part of our common way of thinking. And it's only later on that we started supporting interfaces the way Java or C# provides those. Second point is it was designed as a general purpose language. It was not designed as a domain-specific language. It was not designed to say, well, we're going to deal specifically with this kind of application. We wanted this to be, I say we because it's something I talked about with quite a few of my friends and colleagues, but it was designed to be as universal as possible. Because of my history, because of my culture, the syntax is more inspired by Pascal and modular than C and C++. And to make a long story short, it means that we're going to use keywords rather than braces in a number of places. And this is a typical piece of YAFL code. And I guess it's what it does is fairly straightforward. That gives you an idea of that gives you a flavor of what the language feels like. Something that was really, really important to me is strictness. I have a few slides about strictness, but I wanted the language to be strict. I wanted my point is that anything you can do to protect the developer against his own flaws, against his own mistakes is good to go. Whatever you can do to make the language stricter is going to be helpful, even if sometimes frustrating in the short run. Today, it's not that much of a controversy, but 30 years ago, the fact that we could write production-level compilers by generating intermediate C code that was then compiled was not obvious. YAFL, which is to some degree a similar language designed a few years before that by Bertrand Meyer in France, showed that generating C code was actually workable. So that really was, one of the early ideas. I want the thing to be easy to implement, and that means that we should be able to compile it by generating C code out of YAFL. The implementation happened in 2 stages. So first, my master thesis was reasonably well accepted, which was nice, I have to say. Well accepted enough to have a student the year after implement the first YAFL compiler, writing in C, Lex, and Yak, so the most bare-bone tools possible. And the year after that, having another student use that first compiler to bootstrap YAFL, so that now the entire YAFL toolset is written in YAFL. The compiler was, and to a vast degree still is, a very primitive matter. I don't know how much you've looked at real-world compilers, but there's a lot to be said about having intermediate representations. And at that time, and I take no pride in this because this is like a flaw, this is a mistake. I just did it stupidly because I didn't know any better. But it was, and as I said, still is to a vast degree a very primitive compiler. We take the syntax, we generate a parse tree. The parse tree is analyzed, annotated, and then we serialize C code out of it. It's too primitive, and there are a number of things that we would like to do on the compiler that were not possible at the time, and some of them are not even possible today. Something else which is very important to me is the fact that I wanted to have a garbage collector. As a matter of fact, I don't understand how still today in 2020, I still have to make the case. We need a garbage collector. We as developers have intrinsic limitations, intellectual limitations, and anything we can do to simplify our work is welcome. A garbage collector is the first thing we should do. The first thing we should aim at. And more specifically, we use a precise garbage. Are you familiar with garbage collectors, or is that totally blurb to you guys? Okay, I'll assume whatever answer I feel like assuming, because I didn't get much.
They should. Well, we didn't see how to implement them, but they should know what it is. Actually, they're probably more familiar with the garbage collector than with manual memory allocation. They do some C though.
Okay, so a precise garbage collector is, so let me rephrase this. A conservative garbage collector is a system which at some point says, oh, I don't have enough memory, but it doesn't keep track of anything. What it does is that it says it doesn't have enough memory, so it looks at the stack, it looks at the global variables, which are easy to identify, and scans them and looks for anything that looks like a pointer. A conservative garbage collector is something where it doesn't keep track of pointers when it needs to look for pointers. It goes in memory and says, oh, this is a probable pointer. I'm going to consider this as a pointer, and then recursively reapply on whatever is pointed by that pointer, even if in some cases you may get it wrong. In some cases, you may think it's a pointer, but it's just a bit pattern that happens to be something totally different. In practice, conservative garbage collectors work magnificently. In theory, they are really risky because it means that they can get things wrong and they can fail to deallocate stuff that they should otherwise deallocate. So my garbage collector was is precise rather than conservative. So there is more overhead because I keep track of whatever is accessible at any given time. But it guarantees precision. It means that I do not keep something in memory for bad reasons. And it's also a bespoke garbage collector in the sense that we didn't use a third party. There are a number of third-party garbage collectors available out there. And this is, and we implemented our own garbage collector, essentially for no good reason, just because we didn't know better at the time. I told you about strictness. What do I mean by having a strict language? A strict language is a language where we enforce good practice rather than just encourage it and allow the user to do otherwise. And that's what I call the evil side of pragmatism. In other words, if we say, oh, go-to statements are bad, we say, well, if go-to statements are bad, let's not support go-to statements at all. If we say, I don't know, public attributes are bad, let's not support them at all. And that's really the idea, because leaving that to the developer, leaving the decision to actually enforce those good practice to the developer means that you always run the risk of anyone saying, oh, I really need it now. Everybody can be deluded into thinking that the problem at hand is worth the trouble and can go against it. If we think these are good practice, this practice should be enforced and not just encouraged. That's really the idea. In practice, what does it translate to? First, and the most obvious one, is strong typing. Interestingly enough, when I asked the question about the language for the coming 30 years, strong typing is one of the things that allows you to keep your software running for longer. I'm happy that no one came with Smalltalk as an answer, for instance, but sometimes people come to me with Python or JavaScript. And to some extent, by the way, Erlang comes into that territory as well. Strong typing is the most obvious way of strictness. It ensures that your language guarantees that a number of mistakes cannot be made and will be reported statically. The second part of strictness that we enforce absolutely is structured programming in an absolute total way. Obviously we have no go-to, we have no local go-to, we have no global go-to, we have no implicit go-to, because if you think of it, exiting a loop from the middle, that's a go-to. A return in a function is a go-to, and the list goes on and on and on. We say, no, we think structured programming is the right way of doing it, so we have no go-tos at all, which means that blocks and methods have one entry and one exit point. Anything else would be a violation of the structured programming. Everything has a default value. So whenever I declare an attribute or a local variable, it has a default value, so that guarantees behavior, even if I go from one platform to another, or I change the C compiler, or anything happens. For instance, any one of you who has done serious work, for instance, on C code, knows that it can be extremely frustrating because you have a bug in the C program, you run it into the debugger, and guess what? The bug disappears, because the bug can be very sensitive to uninitialized stuff. Having a guaranteed deterministic behavior to us has shown that when we debug YAFL system, it has literally never happened in 30 years that we had a bug that disappeared when we started debugging it. So we have absolutely deterministic behavior. And we say attributes are always private. Everybody tells you that's the way things should be. Why should the language allow you to do otherwise? So we say, no, attributes are always absolutely 100% private, and you have to use setters and getters. We do have, and I'm going to have a word about this later on, we do have a way to optimize those setters and getters at the later stage of the optimization so that we can have the same performance as if those attributes were public in some cases, so that we don't have the penalty of having setters and getters. But in terms of methodology, in terms of using abstraction, we have an absolute guarantee attributes are always private. In other words, the only thing that can actually change the value of an attribute is an assignment statement found in the scope of the method where is an assignment statement where in the scope of the class where the attribute is defined. And there's more strictness. All methods are virtual. This complicated idea of this one is virtual and this one is protected, and this one is virtual, this one is final. We make none of these. We say, listen, everything should be virtual because that really is a low-level implementation thing. We do not support overloading of any sort. You're familiar with overloading, I assume, right? You've done Java, you've done language with overloading, right? Again, I'll assume this is a yes. This is going to be fun, though. So overloading is the capability of having multiple methods having the same name and different signatures. And it's generally considered a convenience because it allows you to define multiple methods that are really related to each other, that do essentially the same thing with different sets of parameters. And with YAFL, we do not support overloading of any sort because it really using overloading appropriately depends on the developer actually following that guideline. The developer actually saying, well, I'm overloading this because it is indeed adequately related to each other. More often than not, overloading is misused because people cannot come up with new names and they think they're being smart reusing names all over the place. So no, we have no overloading of any sort. A method is identified by its name and its name is unique in its scope. Redefinitions are explicit. When I redefine a method, I must say explicitly that I do redefine a method, and the names and types of the parameters must match exactly. Interestingly, we support covariance on return type. I think I have an example here. And the idea is that if I have a base class where a method returns any kind of type, I can have a derived class where I can redefine the method and return a more specific class. In this case, the shape has a bounding polygon, and a circle say, well, my bounding is more specific than a polygon is a square. And if you look at it and you can play with it a little bit, you will soon realize that it's 100% type safe. And very typically, one of the things that YAFL guarantees to you absolutely is dynamic dispatch. When you call a method, you cannot say, oh, I want the version of this method as written for this class. No, you just have dynamic dispatch. It cannot be overridden. So you have a very straightforward and very linear execution of your code. Strictness. Interesting case. Parameters are always passed by value and they're always read-only because at the end of the day, we want to be as close as possible to the mathematical paradigm. Parameters should not be changed. We do not see parameters as local variables that receive a value. Parameters are parameters. They are passed by value and read-only. And then people say, yeah, what's the point of that? But this is an interesting benefit of it. Say I have a function. So this is the C representation of a piece of code. This is theoretical, but I think it shows the idea. I have my garbage collector, and my garbage collector keeps track of my values at any point. I enter a function, I have a parameter, I need my garbage collector to be aware of it. If my parameter is guaranteed to be read-only, I can do exactly this. I can do something as stupid as saying, well, you know, my parameter is never going to be changed. So I can just take the value of the parameter and say, I want this value to be kept track of by my garbage collector at all times. In opposition, if my parameters was not read-only, I would need my garbage collector to keep track of the address of the parameter. Because guess what? The parameter could have been changed. And if it has to be changed, I need to be able to get there. But, and you see, oh, does that make a big difference? In practice, it does make a big difference, because when you take the address of anything, then you know for a fact that this parameter will not be optimized in a register. Because when you take the address of something, well, the thing must be in memory. That's it's called life. So for this to be at all possible, it means that you force your parameters to go in memory. While on the left side, because I know that they're going to be passed by value, I only read the value, ergo the C compiler can optimize it in a register. Does this make sense? Please ask a question, do something, because I'm going to run out of breath before you know.
Could someone explain what is the difference between by value and by reference? Because I'm not sure that's a clear distinction for them.
You mean someone? You mean me?
I would like a student to explain, if possible. But if no one steps up, then you can have a go, Darius.
No, that's okay. Okay. Anyone?
Is it possible that by value is taking the value and not taking the address in memory? And then if you return the value, there will be just the value, not we cannot change the value in memory just by giving the value.
Yeah, to a vast degree, that's exactly it. I mean, you are going a bit too far, because you're essentially saying that by reference it's going to be in memory, while in theory you could fantasize about having things by reference being passed in parameters, but in practice you're 100% right. That's exactly it. When you pass by value, for all practical purposes, you the value you pass is given as a copy and cannot alter the original values, that the original variable that was passed. When you pass by reference, you're not passing a value saying, I want the call procedure to be able to write in this variable.
I will add some detail because this is often confusing. So by value and by reference doesn't mean you make a copy. So in Java, everything is passed by value. Even though you're passing objects, so objects are essentially pointers, right? So you're passing pointers, but you're passing them by value. And what that means is that you cannot write where the object is being pointed at and change the object. If you get an object, you cannot replace it by another object, but you can change things inside the object, of course. Okay. In C, you could pass a pointer to a pointer and write that. Okay. Does that make sense?
Yeah, to me it does.
To you it does. No, because when you say by value, people imagine that they get different ideas, because it's an intuitive that objects are being passed by value.
Yeah, because the value of the object is the identity, not the content.
Yes, exactly. The value of the object is the identity of the object.
So the only statement, and why do I do this? It means that at the end of the day, I say, listen, the only thing that can change an attribute or local is an assignment, which means that if at some point I say this parameter or this local variable has a value I cannot explain, I have a local track of where can I possibly change this attribute is local. And it improves predictability. And as I showed in a number of cases, it can simplify the garbage collector as well. I know that some of the most modern version of C#, I don't know whether Java has followed suit, but allow you to pass parameters by name and write something like this, for instance. I mean, this is YAFL code, where you can specify the name of the parameters explicitly as part of the call. When you do this in YAFL, Ada supports this, and Ada supports it in a way to allow you to pass parameters in any kind of sequence, any kind of order. In YAFL, it doesn't. It still enforces the order. It's just documentation. But when you set a name of a parameter there, saying I want this parameter refers, I mean this value, sorry, refers to this parameter, the name of the parameter is checked for compliance. This also shows in syntax. It's a very simple thing. It's as minor as can be. Two Booleans can be compared using an ad hoc operator if and only if. Because comparing Boolean for equality with an equal sign is really, it's mathematically true. It's computationally true, but it does not reflect what you're essentially trying to do. Two Booleans being equal is a very specific thing. It means they're both true or both false. And so having these kind of operators means that we do not compare Booleans the same way as others. And that I really think that's a very valuable thing. For me, for instance, I don't know whether Java I should try that, but I know that in C, since there are no Booleans, you can write if A smaller than B. And A smaller than B essentially means literally B and not A. But small is, so we really want the syntax to reflect the intention as far as possible. Similarly, we've got the same with implications. I know that implications can be written with conjunction, disjunction, and negation, but this is, we want the expression to be as clear as possible when expressing these kind of logic. And there are a number of places where we are a little bit less strict. What I mean by that is that, say that you have these complex passing parameters and you elaborate complicated stuff before calling it. If I can realize that my method there doesn't do anything, which is easy for me to assess. I mean, if I have my global optimization capability, I say, oh, my method does nothing, then I will accept as an approximation, I will accept that I'm not going to evaluate the parameters at all, based on the assumption that if you need the parameters to be evaluated for the side effects, then it's something explicit you should do by actually calling these parameter evaluations explicitly and say, oh, I want to call a.b parameter because I need the side effect. I'm going to call p.getType.abstractInfo as a separate one because I need the side effect. So if you write it this way, we assume that if the core of the problem is meth, if meth is not doing anything, we may as well optimize it away. Where can I do this? I can do this if the call is monomorphic. In other words, when I can statically ensure that obj.method only calls one version of the method, because dynamic dispatch cannot be overridden. So if there are multiple versions of it, well, if there are multiple versions, I don't know which one is going to be, so I cannot make any assumption. If it's monomorphic, there's only one version. I know what that version is, and if that version is empty, I can then assess that this call is not going to do anything. It can be empty or it can be made empty because YAFL provides you with a capability like this one, a debug construct that allows us to have code in the source that will only be used for debugging purposes and that will be removed for production level. So when we compile for production level, this method, for instance, would become empty because the debug code, the debug block will be removed altogether, which means that whenever I call this method and if the call is monomorphic, I can then say, well, that code does nothing and I can remove everything. I can remove the call altogether. So I told you in the beginning that YAFL had a pretty primitive compiler, and it definitely is a primitive compiler. Just for you to get an idea of what it can do for us, it means that integrating into the operating system is trivial because we have a capability of producing inline C code, just the way I'm showing here. And for instance, if I need the capability of computing the length of a file, I don't have to reinvent the wheel. I can use the standard C library to do this, and I can insert calls to C in my YAFL code using this paradigm. And there are ways to access parameters. There are ways to access attributes and so on. I mean, this is fairly straightforward. We can take it a step further. We can even have a method where we say, well, if you want the thing to be optimized, you can inline it. And inline it in this way. Inline in this way essentially means that, well, whenever you call this method, you just paste this piece of text where cardinal 1 will be replaced by the first parameter and cardinal 2 will be replaced by the second. Any one of you who has ever played with C knows that this is obviously only valid for functions like this one, where each parameter is evaluated up to once. Because if your parameter is evaluated more than once, this paradigm cannot be used as is. But this allows us to write, let's say, high-level code and to ensure that when it comes to deployment, we're going to get top-notch performance by having something as fast as if it had been written natively for the platform. We even have more sophisticated inlining capabilities. I'm not going to get into the detail of it, but there's really this idea where you say, well, say I have a list and I want to ask for the last element. This piece of code will allow me to inline the access to the last element of a list, which will be significantly faster than calling the function that does it, because this is something we do literally millions and millions of times. So inlining it has a significant impact on execution performance. So far you could say, well, this is all nice and dandy. This guy wrote a language. There's nothing spectacular about it. And I would, to a vast degree, I would agree. There is not some. So far, it's a fairly straightforward language, and you could make the case that well, Java is not intrinsically different. C# is intrinsically different, and you could make the argument even that they are better. And I could even agree with you on a number of areas. But there are a number of things with YAFL that are original, that are kind of unique. And the first one is what I, in due time, called the YAFL support. The compiler support. The compiler support really means that the compiler, the YAFL compiler, is not a black box. It is not an external entity that is, we tell you, oh, you're going to use a compiler. Say, no, the YAFL compiler is available as a library, which means that you can take this library and use it for your own tools. You can write, if you are to write a tool that manipulates YAFL code in any way, you don't start from scratch. You are going to start with the library, with the YAFL compiler, so that the lexical and syntactical analysis are done for you. You may even say, well, for whatever analysis purposes you have, I want semantic analysis to be reused. You can reuse it as well. The whole idea is that we wanted the compiler not to be a black box, but to be made of reusable components. And you could refer to this as compile time reflection. And I call it the compiler support, and people ask me, well, why don't you call it reflection? I say, well, because back then it was a novel concept. The name did not exist. Nobody knew what reflection was. And don't get me wrong, I'm not trying to claim that the Java people got inspired by me. My level of arrogance has limits. I know that it has absolutely nothing to do with it. And it's reflection in a very specific sense. It's compile time reflection. There's one kind of reflection which is analyzing a system while it's running, but this here I'm referring to compile time reflection, something where I can write. I can use the compile to analyze YAFL source code. And it was a novel idea back then. I spent a gigantic amount of time explaining that to people because people didn't really get it. In the meantime, Jackpot was a fantastic project for Java that did exactly that, exposed very sophisticated APIs to deal with Java source code, but that project is pretty much defunct. I mean, I haven't heard about it for years. On the C# side, Roslyn does a wonderful job in that area. Roslyn is a fantastic effort to provide similar capabilities. So this idea, which was put in YAFL, and from day one, this is not something that came later. That was really from day one, so 30 years ago. But now is available in other languages. And you could argue that Smalltalk provides similar capabilities. I think JavaScript, if you look carefully enough, will also do that. Lisp dialects as well, and so on and so forth. What has compiler support allowed us to do? It is a pretty potent capability because you can extend you can use the library for analysis purposes, or you can build your own compilers. You can use your own compilers. You can build your own compilers by extending code generation or replacing code generation, or you could even go further and extend the language itself. We have a number of projects that I'm going to tell you about where we say, well, we're going to use the capability of the language to be extended to allow us to do, other things than pure YAFL, but YAFL with a twist. And I'm going to get there in a second. For instance, the debugger, the first version of the debugger really was, I inherit from the compiler, and in the methods that generate code, in addition to generating normal code, I'm generating additional debugging code. The debugger started as an external effort, as an extension on the compiler. The global optimizer went the same way. At some point, we had a complete experiment on native code generation. A very, very gifted student replaced the code, the C code generation by generation of the RTL, which was back then the intermediate representation of the GCC compiler suites, because we speculated that they could be a benefit in performance. So this student actually inherited from the compiler redefined code generation to generate RTL code rather than C code. And Dura is a very specific effort that I'm going to talk about in a few minutes. For compiler support to be at all possible, the compiler must be simple, because the compiler is a library you must be able to interact with. And from that perspective, the very simplistic, the very stupid way, I could even say, that our compiler works has been a benefit, because a simple compiler is easier, you can actually interact with a simple compiler. You cannot interact with a complicated compiler. Doing the kind of thing we do with the YAFL compiler with GCC or even Clang, I wouldn't say it's impossible, but it's really an uphill battle, because they're way more complicated and sophisticated compiler than YAFL is. And interestingly enough, I say, well, bootstrapping, in many places, people say, yeah, bootstrapping is nice to have. It's a demonstration of capability that your compiler is written in the language you're actually compiling. But for us, since the compiler has to be used as a library, it's not nice to have. It's a requirement. We need the compiler to be written in YAFL so that the compiler can become, the compiler is a YAFL component you can reuse.
So I'm not sure the students are familiar with the term bootstrapping. Could you explain that?
Sure.
Or you just did, but
so no. Bootstrapping is essentially means that when you historically, my guess, it started with Niklaus Wirtz and Pascal, where when Niklaus Wirtz developed the Pascal compiler, what he did, he wrote a very minimal Pascal compiler in assembler, because he had an assembler for the platform. He wrote a very primitive compiler in assembler, and then he rewrote the compiler in Pascal. Bootstrapping is the process by which you have to start with an existing language, because you cannot make a compiler out of nothing. You start with an existing language, and the first thing you do is that you write a compiler for your language in your own language, so that at some point you are independent from external languages. And Wirth did that, so that he says, Wirth, listen, I have a Pascal compiler here. It is written in Pascal, so and it's running on one platform, which means that if I need to target another platform, I can cross-compile from where I was. Bootstrapping is a process where you write a compiler for a language in that very same language.
Thank you.
Okay. Interestingly enough, some languages are better suited than others for this. Some people have even tried to write COBOL compilers in COBOL, which is absolute insanity. But insanity doesn't stop people from trying. Oh, over the years, okay, the language has evolved, and I'm not going. This is not a lecture about the details of the language. The first obvious thing for me was to be able to support nested method, a method nested in another method, which is something that was available since Algol 60, and 60 stands for 1960, so that's literally 60 years ago. 61 years ago. And C did not support it, and by matter of, let's say, cultural percolation, Java and .NET do not support them either. I emphasize this because it is a really cool capability. It has an impact on performance, but it only has an impact on performance if you use them. So just the availability costs you nothing. So I cannot, this is literally a capability that was in ancient languages and that has disappeared for bad reason. It has not disappeared because it's a bad idea. It has disappeared because the modern languages we use end up being derived from C, where C was designed as a very low level language and didn't need anything like that. Quantifiers. I'm going to show you what it is, and you can say, what's the point of quantifiers? Well, it's syntax. It's only syntax, but it's fantastic syntax. Support for interfaces, boxing, unboxing, robust connectors. I mean, I can spend quite a few things, quite a few hours about the details of the language, and many of these things are syntactical sugar. The really thing that we do to make the language more comfortable to use. It's not rocket science, but it really makes the developers' lives easier. And this ended up in an updated document, which for quite obvious reason we called the YAFL programming language version 2, which is an updated language definition. And there are many things to say about this entire effort. Perhaps one of the most interesting one is the fact that when I wrote the YAFL programming language version 1, I thought of a number of possible optimizations we could apply. I was so wrong. Literally none of the optimization I thought of when writing tuple 1 have actually been implemented. None. And on the other hand, we came up with a bunch of other optimization that had nothing to do with the one I thought of. Thinking that you can dream optimization in the void is probably exactly that. It's a dream. We had another effort which was very, very successful, which I really like, and it's the global optimizer. So the idea really is that, you know, OO systems are designed to be dynamic and methods can be redefined, and you've got late binding and all these things that are very nice and dandy. But then for a given program actually running, you could say, well, do I actually need this? And the global optimization, global optimizer that comes with the YAFL compile nowadays really is about saying, well, let's take an actual system and look whatever dynamism which allowed by the language has not been used in this specific case and optimize the code accordingly. So it started with a YAFL project and it computes the transitive closure of all the reachable code. You know, so because it's all static, it's a statically defined language. So all the classes, all the methods that are never used are removed. Expressions are simplified whenever possible. We removed debugging code. When a call is monomorphic, when I'm actually calling a method and I can statically ensure that, oh, this call here cannot go to a redefinition because guess what? There are no redefinition. Then I can actually translate the call into a direct function call rather than go through dynamic dispatch. And then I can say, oh, do you know what? What I'm actually calling is a setter or a getter. Are you familiar what a setter or getter is? Is that a yes or is that we don't know?
Yes.
Okay.
Someone even said, of course.
Yeah, you'd be amazed. You'd be amazed. So I apologize. Yeah. I didn't mean this to be insulting. I just wanted to be clear. Sorry. So when you call a setter and getter, the compiler says, "Oh, this is just a setter and getter." It recognizes the form of a setter and getter. Oh, this is just a setter and getter, and it optimizes the call so that the code gets as fast as if we were talking about a public attribute, and so on and so on. So the global optimizer is what's used at the very end of the development before delivering the process, a binary to a customer. This is how we produce a compact and optimized binary. And this is a very common pattern. The first version of the global optimizer was external, was developed as an extension of the compiler using the compiler support capabilities. And when it proved to be really good and useful, it has been integrated back into the compiler. So let's talk about more recent evolutions. And some of them are, you're going to say, well, these are details, and you could have a case. There are indeed details. One is integrated unit testing. I look at what people do with Java and C# typically with unit testing, and they have separate projects for tests. Also, you have a main project and you have a separate project for test, and then you have libraries, and then those projects become more complicated. The testing project become more complicated, and then it's an extra effort. And with YAFL, we thought at some point, I mean, as a matter of fact, to be totally candid with you, that was not even me. That was my colleagues came to me and say, we want unit testing. And then say, well, my colleagues want, so they probably have a point there. So I say, well, I'm going to do something about it. But I looked at the way other languages did it and say, well, if unit testing is important, and I think it can be absolutely important, I want it to be part of the language. I don't want it to be run as a parallel project on the side. We have enough projects. I mean, if you look at our environment, we have dozens, perhaps 100 projects. I don't want to have 200 projects because for every project I need a testing project next to it. So I wanted something more integrated than that. And what essentially we have is that we have classes which have to inherit from a given base class, and it's called YUnit. And you have methods that start with test and that do unit testing exactly in the way you would do them with Java. This is very similar to what you have with Java. And these things are just in your code. There is no need for another project to say this is about testing. Every module that contains a number of classes can contain one or more unit testing classes. So it is a more integrated variation on JUnit because there is no external asset required. Everything is directly in the code. And when I run a system, I can say, do you know what? Instead of running the system, instead of doing whatever you want to do, run the unit test attached to the project. All the relevant tests, which means that, interestingly enough, if your project uses libraries, all the unit tests of those libraries will be tested as part of the process. And typically, so you say when I run a YAFL system, I have a specific command line, which is your application doesn't have to deal with it. This is something that is dealt with directly by the YAFL runtime. If this command line is, if this kind of option is set, then instead of running the program, it runs the unit test. And you have something which is very similar to what you would have with other languages nowadays. And the whole idea is that if you if you are developing in, if you are in debug mode, then all the tests are kept. If you are producing a globally optimized version of your system, by default, all the tests are removed so that they do not bloat your resulting system. And we have specific options to force to override this behavior, whether you want to remove them in debugging code or force having them in global optimized versions. So this is like not rocket science, but this is very typical of the things we do, is that if we say, well, if unit testing is important, rather than say, oh, we're going to do it as a parallel thing and with another set of artifacts, we'll put it in the compiler, in the runtime, in the language as thoroughly as possible. So this part I'm going to skip. Don't get me wrong. This is absolutely fantastic, but this is going to take like another hour in its own right, and I don't think we can afford it. So if it's okay with you guys, I'm going to skip this. It's really fun, but it's a little bit too time consuming for comfort. So where do we get with this? So I told you in the beginning that my ambition was world domination. Well, I think it's an understatement to say it didn't work as expected, right? I'd love to say that many people are using YAFL nowadays. Obviously, that's not the case. I'd love to be able to say that I became a billionaire out of this. I did not become a billionaire, and if I did, it would not be out of YAFL, obviously. We got a number of kind of reactions. People say, what's the point? For instance, people say, yeah, Ada is going to take over. What you do is pointless. Other people say nobody should be in the business of developing languages. You should go for industry standards, because, people come to us and say, oh, everybody uses Power Builder. Why don't you? None of you. I'd be very surprised if anyone in the audience has ever heard of Power Builder. 20 years ago, it was like the thing. That's what people use to develop application, and now it has pretty much disappeared. And interestingly, people told me your language is annoying, and this is where you realize that as I told you in the beginning, I wanted the language to be strict because I see this as being part of the added value of the language. Strictness is a feature; it's not a bug. it's designed to be strict because it makes for better software systems. And if you try to convince people to use it and they say, oh, it's annoying, we would like you to make it more comfortable there, it's complicated. So obviously acceptance didn't go the way we wanted. We had a number of early adopters. We had a number of customers, but like a small number, single digits, literally. But essentially, we were the best customers. YAFL has been used internally for the last 30 years. And I have to say that still today, I'm very grateful to my business partners because now in retrospect, I'm going to explain you why in a second. It obviously was a very good idea. But back then, nobody knew, and I definitely didn't know. And essentially, because they're good guys and they're good friends of mine, my business partner said, well, let's go for YAFL. Let's do this in YAFL. Again, you know, common wisdom, against naysayers, against sometimes their best judgments. They accepted. I'm really very thankful to my business partners for allowing the YAFL story to have existed in the first place. And then we came up with two breakthroughs. World domination didn't happen, but the YAFL story is an absolute success, and let me explain you where and how. The first is the day we consciously said, well, you know, world domination is not going to happen. Let's stop fighting this. Let's stop even try. We said, you know what? We are essentially going to give up. I'm glad to tell you the story about YAFL. I'm not going to spend a second of my life trying to convince you or anyone that you should use YAFL for your software development. I don't have time for this. To a vast degree, it is us saying, well, you know, we think this is the way software should be developed. You want to do otherwise? That's your loss. We move on. And essentially, seeing this as being an industrial added value and not an evangelizing effort is really much better advice than generally assumed. We don't try to convince anyone, and some of you may not be convinced by this story, and that's absolutely fine. I'm fine. I'm telling you my point, and I move on. But I'm definitely not in the business of expecting anyone, big corporations, the world at large, to start saying, "Oh, we're going to use YAFL as a programming language," which means that we are the install base by now. We have, I think the last figure is just under 2 million lines of YAFL code in production. That's the install base. That's what we have to care for. And we don't have to care for anything else. And as I say, we believe it's the best tool around. You don't, your loss. We're good with that. But we don't lose time trying to convince anyone. But what's interesting, for instance, is the fact that backward compatibility is under our control, 100%. When I do a change to the language or to the compiler, say, oh, hold on, it may break things, I only have to care for those 2 million lines of code. If those 2 million lines of code pass, or even, oh, they don't pass, but there's like half a dozen things I have to change manually, I change them manually, and we are good to go. I don't have to worry about the world at large, people in the wild saying, oh, my YAFL compiler doesn't behave the way I wanted it. There is no such thing. So this has given us a fantastic freedom because we are a master of our destiny. We know exactly what's what and where's where. And to give you the exact opposite, I mentioned YAFL a little bit before by Bertrand Meyer. Bertrand Meyer never gave up about world domination. I mean, he came up with YAFL, which was a fantastic effort. And he still today thought that he should convince people that YAFL is the best language around and everybody should develop in YAFL. I think it's doubtful. B, he didn't realize, and I don't think he still does not realize, that all these things have at the end of the day little to do with the value, the quality of the language, but tons of other factors. In other words, I think, for instance, that Java is okay, but okay at best. The fact that Java has crushed the C++ market and has crushed a significant part of the programming language market at large doesn't mean that Java is the best. If you think that, you are missing the point entirely. It has come from a variety of factors. It has to be technically adequate, but it's by no means the best effort at all. That would be a total fantasy. So in other words, world domination when it comes to language comes from a number of factors, chance, luck being an important one. Bertrand Meyer, at some point, he he managed to have like 2, 3, 4 competing implementation of the YAFL language. So in that sense, you could say he was more successful than I ever was. Absolutely. But the point that he lost is that he said, well, when there are competing implementation, when you have an install base to care for, you don't get to choose. And he at some point said, oh, I would like to make a significant change of my language. And he made a number of changes that were probably good idea in theoretical terms, and that the competing implementation could not match. And YAFL has died in 5 years because of that. He had, not the large, but he had an actual market. He had a number of people that were following the YAFL gospel, if you take. And these people have gone away essentially because, well, he didn't care enough, and he didn't understand that he didn't have the freedom to do whatever he wanted because the install base was something to take into account. And that's the whole point. We don't have an install base. We forget about world domination. I don't care to convince anyone. I am my own install base. All I have to care is our own piece of software. Which means that we focus on what matters to us. The language is as strict as we want it to be. If we could make it more strict, we would. We focus on syntactical sugar because we think it makes a big difference in terms of productivity, in terms of comfort for the developer. We focus on portability a lot. That's why we generate C code. And we're probably going to stick to that for the foreseeable future because that's our guarantee of portability. Whenever we aim at the platform, if the platform has a C compiler, we're good to go. And we remove absolutely everything else. Everything that is not 100% what we need, we don't care for. At some point, when we were still having the deluded dream of, going after the market, we say, oh, we need to be able to develop graphical user interface applications with YAFL. And we tried that, and we invested fortunes, and we never made a dent. It's impossible. This is a market that we have nothing to do, and we don't stand a chance. It's an arms race dominated by people that have way deeper pockets than we have. We don't try that. We stopped doing GUI support altogether. Said, you know what? If we need GUIs, we'll use other tools. YAFL, the value of YAFL doesn't lie there. Similarly, native code generation, I told you about it. So we had that very bright student that implemented native code generator. He managed in very idealized cases to get a 7% performance improvement, which wasn't bad if you think of it, but the dependency was too toxic. Depending on the GCC's RTL infrastructure was a toxic proposition. And we were right to say that because guess what? Today, GCC's RTL has disappeared. So if we had gone there, YAFL would no longer exist. So there's that. We focus on what matters to us because it's just about us, and it means that YAFL, we now value YAFL based on its technical benefits for us. What it does to the rest of the world, we don't care because we don't serve the rest of the world. The other part that has been a true breakthrough with YAFL, that has turned YAFL from, say, an anecdote to an industrial enabler, was Dura. Just for you to know, Dura doesn't mean anything. It's just that it has to do with programming languages. And there is a Unix tool called sed. There's a Unix tool called lex, and I want to have Dura lex, sed lex, so my tool is called Dura. That's it. It doesn't mean anything else. And the idea really is to say, you know what? We write compilers. That's what we do for a living. And when you write compilers, we write parsers. I assume you've seen YAC, right? You at least have some familiarity with YAC.
We haven't seen YAC per se, but we've talked about LR parsing in the course.
Okay.
But they haven't seen the syntax.
Okay. Good point. So if you use YAC or TLR for that matter, or virtually any other system, what they have is that they have an external grammar file. The grammar is an artifact. The grammar is an artifact from which you generate a parser, and then you write your code to interact with that parser. And that will work, but at scale, that thing is going to break. At scale, it gets into a management nightmare. So what we did was to take it the opposite way. Said, you know what? I'm going to take my compiler, and in my compiler, I'm going to support extensions. And one of the extensions will be to say, well, you know what? A class is not just a class. It's a non-terminal class. And that's what you see there on the slide. And when I have a non-terminal class, I have a grammar rule. And this grammar rule contains reference to keywords and contains references to attributes. Which means that such a class comes with a grammar rule, and the parser generator can then scan those grammar rules and generate the parser. But the parser is not just a recognizer. When you use YAC, you will see that if you ever do, YAC doesn't produce a parser, it produces a recognizer. It tells you I'm recognizing the input, and at some specific point, you say when you'll have recognized this, execute my code, and the code you will write more often than not will be about building a parse tree. And that works, but again, it will not scale. So the Dura capabilities goes in the direction of having the parse tree generated automatically for you. And it's not just a parse tree, it's a strongly typed parse tree, because when I say that the main body is a statement list, you know that what's going to get there is a statement list. It's not going to be a pointer to some kind of vague object. The system is entirely statically type checked. And this allows us to build parsers, to build front end for compilers way more comfortably than any other competing technology today. This is a competitive advantage. We write compilers, and we have the best tool to write compilers. I call that the most specialized DSL. This is a DSL. This is a YAFL. I told you in the beginning it was a general purpose language, and that really was the idea. And Dura turns this into a domain-specific language to write compilers. And by the way, this is how I got my PhD thesis. My PhD thesis was entirely about Dura and the tool set and demonstrating that it actually works. And just for you to know, that was 20 years ago. My PhD thesis was 20 years. So there are many things to say about Dura. A is that we have a very comfortable formulas to express grammar rules. Interestingly enough, they are modular, because when you deal with YAC, one of the problems comes from the fact that your grammar file is one grammar file. It's one grammar. And again, when you have a small language, it works fine. When you have a large language, it becomes an issue. Because YAFL is granular, and because grammar rules are identified as specifically written classes, you have intrinsic modularity for your grammar. So that gives you scalability. And if you think it's a joke, look at this. I submit that our COBOL parser is the largest parser in the world, literally. Our Lexer has over 11,000 states. I don't think that Unix's Lex can even take that long. If you use YAC and Bison, you talk about LR parsing with the LR states. A typical YAC and Bison parser will get you a few hundred. We have over 17,000 LR states. So that part of this has to do with the fact that we deal with industrial cases. We do not deal with simplistic languages that you use when studying. We deal with real-world languages, and they can be incredibly large and incredibly, incredibly ugly. And then there are a number of funky things. For instance, we support lexical backtracking, because in PL1, for instance, and Fortran is the same, but to some degree only. But in PL1, you have no reserved words. In PL1, you can name a variable if. I know it's idiotic. I'm not saying it's good. I'm not saying that's the way language should be done. I say, well, the PL1 designers did it this way. And I have to process PL1 code. I don't get to choose. I can't get to my customer and says, oh, yeah, but you cannot use that. We have millions and millions and millions of lines of code. We cannot change them. So we have to support this. And interestingly enough, not only does PL1 support a variable called if, but even if the variable is not defined, it will define it implicitly on the first use. In other words, the very, very stupid statement I write this is valid in PL1. And our parser generation capability can process it, can deal with it, because we have lexical backtracking. In other words, at some point it's going to say, well, if is a keyword, that's good. and then it's going to bump into the second one, and it says, well, if is also a keyword, and say, well, I cannot do anything with it because I cannot have an if keyword following an if keyword. Can your second if keyword be something else? And the lexer will backtrack and say, well, yeah, the second can be an identifier. Then say, oh, good. If it's an identifier, I can proceed. Then using lexical backtracking, even a statement as idiotic as this one can be parsed efficiently and effectively by generated parsers. We also have syntactical backtracking to address ambiguities. And essentially, if you've seen LR parsing, you've seen shift and reduce. The whole idea is that we have the capability to do unshift and unreduced. At every given position, instead of saying I have one action to choose, we have a number of actions. And if the first one doesn't work, we try the next one.
They've actually implemented a grammar that uses backtracking, like using parsing expression grammars.
Okay.
So they should be familiar with that.
Wonderful. And we use parsing expression grammars in some areas, but scale-wise, it doesn't really compete. It's scale-wise, there's something when it comes to very large grammar where PEG parsers will probably collapse.
You should use my tool. I have some ideas about that.
Yeah, as a matter of fact, one of our best engineers comes from the UCL, has implemented a PEG parser, and it does work extremely well when it comes to. So it scales well on the size of the input. It scales so and so on the size of the grammar because the PEG formalism doesn't scale all that well. At least that's our perception of it. There is more. Let's not get into the details of what Dura is, but this is the idea. The idea is that, well, instead of using YAFL as a third generation language, we specialize it using the compiler support so that we can actually process, we can include a parser generator in the tool set. And we take it a step further. We integrate the object model in the grammar. If you have something like this, where you have a base class, it's a non-terminal, which is a statement, and you have derived class, and I think this all makes sense, right? You've got an if statement, a while statement, assignment. The fact that you have that inheritance relationship will translate automatically in your grammar into something along those lines. We refer to this as reverse inheritance, where the grammar rules where the base class inherits from the grammar of its derived classes. And if you think of this, type-wise, this will work. If I have a lift statement, these statements can be if statements, while statements, assignment statements. In other words, this disjunction is type-wise correct. Does this make sense so far? Any question?
Makes sense to me.
Yeah. Any question? If only as a matter of mercy, so I can, get some breath.
I have tons of questions, but I think I maybe hold them till the end and give the students the chance to ask some questions as well.
No questions so far? Okay, so no mercy. Let's move on.
Do you want one question? Because I said,
sure.
I have many.
Yeah, shoot one.
What do I start with? Okay, you said at the start that YAFL privileges abstractions over optimization.
Yeah.
But then you did talk a lot about optimization also, like you have a global optimizer, etc. And so, what's the role of performance in YAFL? Do you have some requirements there specifically, or is it just faster is better in general?
You're raising a very valid point. As a matter of principle, as a matter of fact, I think it's even my very last slide. I try not to be obsessed by performance. I think that we look at faster is better as a matter of principle, and it's not always true. But when you start doing production level work, to put it differently, what's important is not necessarily performance, it's the ability to optimize. Those compilers are used by hundreds, by thousands of people. If they are too slow, it is a problem. It really is a problem. We deal with extremely complicated optimization process. Let me rephrase this. The YAFL compilers implement highly complex optimization algorithms, and if they are not implemented adequately, it really is a problem. We use YAFL to implement interpreters. So the interpreter is written in YAFL, which means that any gain of performance we get at the YAFL level translates directly to the interpreted language at hand. In other words, I personally, I try not to be obsessed by performance. And then sometimes people come to us and say, well, this is all nice and dandy, but we need, and they don't come and say we need 10%, we need a factor 5. And then you know that your life is going to get miserable. So in other words, with YAFL, what was important in what became important, because I really tried to fight it off in the beginning, was to say, well, it's not important that we optimize everything. It's important that we have the ability to look at specific parts and figure out ways to optimize them.
Okay.
Interestingly enough, when it comes to optimization, one of the most potent optimization we could do was on the garbage collector. Let me take this a step further. When you have a non-trivial system that really allocates a lot of objects, and that's really happens more and more. You know, we generate millions of objects, and we have like hundreds of garbage collector generation. One of the best way to optimize it is not to look at the language, not to look at the code, but to look at the data and see whether we can compress the data in such a way that we use less memory. And by using less memory, you run the garbage collector less often. And this is where you can get gigantic factors. It's not a common occurrence, but we sometimes see systems that spend 70, 80% of their time doing nothing else than reclaiming memory, which means that working on data can be more potent than actually working on code.
Okay. I can't resist asking another question, which is very related. So you were talking about using GCC, the RTL as a backend.
Yeah.
Have you considered other backends? I know you're working with C# a lot, so you could, for instance, generate the C# intermediate language for the Microsoft intermediate language.
So we envisioned a number. When we did that GCC thing, a number of things were not clear in our minds. Since then, we know that a significant part of the benefit of YAFL for us is that we are master of our destiny. That we do, the only thing we depend on is a C compiler. If we started generating for the CLR, which we do in other circumstances, but if we'd say, well, YAFL is going to generate CLR code, we would then induce a dependency that could become a risk factor. I'm not saying it will, but it could become. To be totally candid with you, that's only part of the story. The more important part of the story lies in the fact that there are a number of things in YAFL that are not well designed to go to the CLR. The semantics of strings is not adequate. And when I say I'm not adequate, I'm going to be even blunter. I think Java and C# got it right. And when I designed YAFL 30 years ago, the semantics of strings I put into YAFL was wrong, but we're still suffering from it, which means that if we are to support the CLR, we first need to make a serious change to the YAFL as a language, correct our 2 million lines of code accordingly. It's a multi-month, perhaps multi-year project to get there. But we thought about it, but it's just, yeah, it's a lot of work, really.
Yeah, I can imagine. Now, because I was going to say, one benefit of doing that is that then you get some quality optimization from that. I'm not sure how C# does an optimization, but for Java, the GVM is very good. But what you said before made me think that maybe you don't want that, because then you lose control. So you get good optimizations, but you cannot control them really. So that trick you were talking about, compressing data to speed up the GC, you can't do that anymore, obviously.
A, you can't do that anymore, and B, at the end of the day, people think that so Java does a fantastic job at optimizing what they do, and don't get me wrong, I think what they do is absolutely fantastic. But they cannot beat us on performance, because you know what? We control everything. And C code on low-level stuff will beat Java code anytime. The Java optimizations are really good at optimizing things that you cannot express in a low-level fashion, and they recognize things that can actually be mapped to lower-level stuff, and they do a fantastic job there. But on the things we do, they can't beat us because we're already as low as we need to be. If we go to Java and C#, interestingly enough, it would not be for performance, because for performance we are good to go. It would be more for interoperability, the ability to write YAFL code that interacts with external, .NET or external Java systems, which could be a very valid reason to do it. But performance is not the main concern.
Okay, that's interesting.
Oh, you know what? I feel like a quiz. Okay, you guys. So let's say you have to write a compiler. I'm not telling you it doesn't have to live for 30 years, but you have to write a compiler. What language would you use to write a compiler?
C++, C.
Okay. Okay, I apologize because I'm cheating. Anything else in C++ and C?
Someone said Python, Java.
Okay, okay, the C++ and
C
C.
assembly.
Okay, never mind.
Assembly.
Okay, so
yeah, there are some troll answers.
That's okay. You might as well have fun. That's fine. So I apologize. I'm going to ask a follow-up question. Why C++? Whoever answers C++ or C for that matter, what makes you select C++ or C?
Be brave. Sorry, and answered performance.
Okay. Okay. So C++ and C allow you to write systems that have very good performance. That's true. Now let me rephrase the question differently. Is a compiler a performance-sensitive process nowadays? The answer is no. I mean, compilation times 30 years ago could be an industrial issue. Today, they don't matter. It's that simple. The speed of your compiler only matters in terms of, sorry. Okay, sorry about that. The speed of your compiler only matters in terms of orders of magnitude. It doesn't matter. Having a compiler being marginally faster is pointless. You don't care. And because of that, you have to take the opposite approach. I don't need performance. I need abstraction. Anything you can do to make your life better, you should take advantage of. For instance, not that I think that Java is the greatest language ever to write compilers, at least it has a garbage collector. Java would, and the fact that it's fast, that it's slower than C and C++ in this case, does not matter. Python, the truth is, compilers are really complicated beasts. I would not go for writing something of that complexity with a language that doesn't have static type checking. That is like, yeah, very, very ambitious and risky, and has, from where I stand, virtually no benefit. But it's, and don't get me wrong, I get those answers all the time. Oh, C and C++ because of performance. Do you need performance? Obviously, I apologize for saying if you disagree, but no, you do not need that level of performance. That level of performance will not really help you. The true word in English would be pointless.
So I'd like to give my answer, which is that I would write it in Java, but because it's the language I'm most familiar with and productive with, and there's no other counterindication. Like you said, I wouldn't write it in a untyped language, for instance.
No, Java could do. I mean, but then sometimes people come to me and say Scala. I say, wait, I mean, I have concerns about Scala, but Scala is at least it's a high-level language, yeah, and whatever, and it could be functional languages. It could be very abstract language. I could be okay with many different answers, but it's really what I'm trying to get at is that when you write compilers, it's all about abstraction. It's very little about performance. That's all I was trying to raise as an issue.
Yeah. So you said something interesting is that it's about order of magnitude. So for instance, people used to complain a lot about the performance of the Scala compiler. It was quite slow. And they improved that, but the way they did it is it's still written in Scala. They just improved the algorithms and the data structures that they're using to improve performance. So it's not about the language, because the JVM can be fast enough. It's about the algorithms.
I mean, Scala is not my domain of expertise, so I'm not going to elaborate too much on that. But
there are a few languages that people complain about compilation speed. But you're right that going from I don't know, Java to C is not going to make a huge difference there.
And more to the point, I mean, let's put it this way: the Scala compiler is an insanely complicated beast. You know, it does like try to imagine writing that in C or C++. If you feel comfortable with it, you're much smarter than I am. I wouldn't dare. It's just the complexity will kill you. At least that's my where I stand. I suggest we move on. So YAFL, and more specifically, it's not YAFL per se, but it's the capability of writing compilers with a more adequate tool has turned into a competitive advantage. It has made our company more powerful. It has made our company richer because we have more IP than most companies our size. Because part of the IP, part of the value of the company lies in software that has been written 20 or 25 years ago. But you know what? Software is not a machine. It does not wear out. If it still works, it still works. There's no counterindication. Software is too often replaced because its underlying infrastructure is no longer available. But we are master of our destiny. It is our infrastructure. And this allows our software to live longer. And this is why we as a company, we have way more IP and way more wealth in this IP than companies our size have. And it has to do because YAFL and our entire toolset is under our control. It is designed to be universally portable. All we need is a C compiler. That today, if you come to me and say, let's say, well, I need to run this on a new platform. If there's a C compiler, we're good to go. And the truth is, if you came to a platform tomorrow, and there's no C compiler, there is work to do. But we could definitely retarget our compiler to another language. It would be more work for sure, but it's possible. We are master of our destiny. So what about me? Oh, but just for you to know, this is not a picture of me. This is a picture I thought would look nice. So I'd love to be so youthful and so elegant with a stick in my hand, but no, that's not me. So I used to be the main designer maintainer of YAFL. I mean, for a long time, that was one of the things I did. I no longer do. I mean, the company has grown. People ask me what my development platform is, I have to answer something between Outlook and PowerPoint, which really depresses me, but that's my life. So some of my colleagues have taken over the work around YAFL, and that's fine. It's nice to know it doesn't depend on me personally, so it's nice to know that it will survive me. And interestingly, many things they did, I do not agree with. They are not what I would do about the language. They are not what I saw as YAFL becoming. But you know what? That's fine. This is not about me wanting things. It's about them using it. And they say, well, we will be more comfortable. We will be more productive with these features. This is what we do, and that's absolutely fine. I'm absolutely fine with the idea of saying, well, you know, they are the users. What should I say from using PowerPoint and Outlook? I should not have a say into what the language goes into the language because I barely use it nowadays. So in retrospect, it has been an immense source of satisfaction. My PhD thesis I told you about. I mean, today we sell compilers where the parser, the front end, is done with Jura, with the result of my PhD thesis. So that's a fantastic satisfaction. To be totally candid with you, how can I say this? I value the opinion of my customers, but I really value the opinion of my colleagues way more. And the fact that my colleagues, which some of them are really among the very, very best and most specialized in the industry, say, oh, this is the way to do this, is, you know, the most important satisfaction. This is really if talk about achievement, that is the achievement. To have those people I respect with no limit inside tell me, okay, this really was a good way to do this. And we have unique products and we sell them all over the world. And that's not the money too. I mean, the money is fine, but it's not about the money. It's about the satisfaction of doing something unique from the ground up that is interesting enough for people across the world to buy. So, what else can I hope for? You could say I could hope to be as elegant as this conductor there, but that's another story, another time perhaps. So lessons learned in the process. The implementation. Implementation matters. Quite often we see people saying, yeah, I'm going to design a language and I'm going to find a grad student to implement it, and say, I mean, don't get me wrong, it's fine to have a grad student implementing things, but the quality of your language will be to a vast degree dictated by the quality of your implementation. The case we mentioned about Scala shows clearly that doesn't matter how good the ideas are, if your implementation doesn't meet up, probably it's not gonna deliver. This is something I said once. I wrote that on an email to a guy. I said, well, YAC and Lex are problemless solution. I really believe this. I mean, the LALR1 restriction is an unreasonable one. In practice, it only applies to so simple language that you could argue those languages are so simple that I don't need a parser generator. I may write a parser from scratch. It would be the same. Interestingly enough, I also see a lateral issue with YAC and Lex, namely the fact that YAC and Lex are designed to work together with C. And because of that, when you ask people what language would you use for writing a compiler, they answer C. Not because C is a good language, but because they want to use YAC and Lex. So YAC and Lex are problemless solutions. Interestingly enough, I sent an email with 2 lines about that to a guy I know, and he sent it to Albert Aho, the guy from Aho Seti Ullman, the Dragon book. And the guy has now an image with me, and he's burning it. He flamed me, say, oh, you don't know what you're talking about, you crazy nuts. I wrote the best book about compilers ever, you stupid, YAC and Lex are great. So I didn't start an argument, but just for you to know that people get a little bit emotional about this. I stand by, I mean, don't get me wrong, Albert Howe is a good guy, he's a smart guy, but he was very pissed when I said that YAC and Lex were bad, were not as fantastic as they thought they were. Early optimization is the source of all evil. You've heard that many times. It's so true. Optimization is necessary. Sometimes you're going to need to improve performance. There is nothing worse than speculating on what you need as performance, where you need performance, and how to address performance, to speculate on this and deal with it preemptively rather than just have something that runs and start from there. As one of my wonderful colleagues says, you optimize a working system, you optimize a debugged system, you don't want to debug an optimized system. So early optimization is the source of all evil. If anything you want to remember, that's like the absolute truth. When you get something wrong in designing a language, it will follow you forever. What I told you before about the semantics of strings being inadequate, and it really is inadequate. Well, 30 years down the road, I'm still struggling with it. So this is the area where some of this you can address and some you can't, and then you're stuck with it. So that's like really hard. And you should always take time into account. What I mean by time into account is when you implement your own language, it's not about what you can achieve for the coming week. It's not what you can achieve about the coming month. It's about how are you going to survive with whatever you do for the coming 10 years. If you do not design your language for the coming 10 years, you should not be in the business of designing language in the first place. Syntax matters. Nowadays, it's a common platitude to say, yeah, syntax is just sugar. And because sugar is bad, admittedly, there is something about to say, well, syntax apparently should not be important. I beg to differ. Syntax matters a lot. Let me show you this, and this comes from an actual piece of code of ours, right? If you look carefully, the last statement at the end of this method is a quantifier where I essentially say, well, for all the elements of the vectors, either they are equal or one of both is nil, which is a direct transliteration of the mathematical formula put beneath. It's exactly it. The fact that I can express it in a way that maps the mathematical representation that closely is a true asset. It's one of the ways for the reader to understand what it does. It's one of the ways for the writer to get confidence that what it does is indeed what's intended. I know I'm not that stupid. I know that you can write the same with a loop and condition and so on, but good luck for making sure it does the same. Good luck for casual reader to understand it. Good luck for like everything. And at the end of the day, if you know how to write a compiler, the code that is generated by this quantifier is just as efficient as the loop, because at the end of the day, it's going to be the very same loop. There is no difference. It's not going to be slower. It's going to be the exact same thing. So syntax, I really believe syntax matters. I already told you that strong typing for now and forever. Strong typing matters. If you are to write code that lives a long time and has to be read and maintained by many people, strong typing is your best friend. Strong typing is what allows you to, what will catch many mistakes you make, is what, and you may say, yeah, but I know this code inside out. I don't make mistakes. I say, fair enough. But you know, someday a poor soul may have to maintain that code, and he or she may not be as familiar as you are, and he or she may make mistakes. And strong typing will ensure that an entire class of mistakes will be caught early by the compiler, rather than requiring lengthy debugging session. An interesting thing I'd like to emphasize, by the way, is that when you talk about typing, people usually talk about consistency. Say, oh, so that you ensure that all the types are consistent. I submit that typing is not only about consistency, it is about documentation. More to the point, I know that all languages across the board nowadays have ways of inferring type. You don't have to say what type it is, the compiler will figure it out. I submit that this is wrong. The purpose of writing type is not just to have consistency, sorry, but to have something written in your code where you say, me, I, as the developer, I know this is what I assume the types to be. This is what I want you as a reader to know about the type of this variable, the type of this expression. So it's not just to get things consistent. It's about a way to document formally something you know as a property of your system. And inference is just being smart and say, oh, you know, I don't have to tell the type. Beep. The type is implied. At execution type, it makes no difference. It makes your source code poor. It removes potentially valuable information from your source code. And some people will even say, oh, typing is all about performance. Forget about performance. Ignore performance. Some of you know about JavaScript. TypeScript shows the benefit of saying we're going to take a language which is inefficient and poorly typed and turn it into a language which is equally inefficient because there's nothing we can do about it, but we're going to add typing to this as a way of improving the quality of the software we write. So it really is barely a matter of performance. It is a matter of quality of the software. And to be honest with you, I just can't believe we have to make this case again. This is 2021. How come we still have to make the case for strong typing? I don't get it. If I were to be able to walk back in time, I would find whoever invented JavaScript and pay millions to spend his time doing something else in his life because JavaScript is a disaster. But that's a different story. So, how much performance do I actually need? It sounds like a stupid question. How often do we ask? We barely ask the question. We say, you know, we measure things on performance, not because we need performance, but because it is easy to measure. How do you measure quality? That's painful. How do you measure robustness? That's painful. How do you measure performance? That's easy. Let's go for performance. But we, as an industry, spend way too much time improving performance on systems that do not need performance. And one of my colleagues has that wonderful, wonderful metaphor where he say, well, we're optimizing idle loops. We are taking something that takes tenths of a second and makes a hundredth of a second, and then but for the guy who waits for that tenth of a second or hundredth of a second, it makes no difference. It's noise. And you see quite often very ill-designed systems systems that are extremely poorly put together because they try to achieve a level of performance they don't actually need. They don't need. Remember the question, why to write a compiler in C++? Oh, I wanted to go fast. Do you need that performance? Well, actually, you don't. This is the presentation per se. We are, I think we still have a little bit of time for questions. And for those of you who are so inclined, I have something I call the bug from hell. It's like 10 more minutes and the story of the worst bug we had in YAFL in 30 years of experience. And I think it's a fun story, but that's up to you guys. Other than that, do you have questions for now?
Okay, I'll ask a question. Guys, just think about your questions, write them down, so you'll be sure to get them in. So, yeah, so the question I have that would be interesting for students is, you were talking about compiling from source code directly to, well, to emitting C, and you said if you were to do it all over again, you would use some intermediate representations.
Yeah.
And this is something we don't really cover in the course. I'm not working on code generation, but we talked about parsing, semantic analysis, and then we'll do code generation and a little bit of optimization. So what kind of intermediate representations would you add, and what do you need them for? If you could explain that.
Oh, you need them because you want to be able to perform analysis that does not depend on the syntactical representation of things. In the course of a compiler, if it can be for optimization purposes, it can be for inlining, can be for many different reasons, you are going to need to analyze the behavior of your code. And in that process, having no other representation than the source code is like the worst, is absolutely lethal. You can do things at the source code level, but it soon becomes really, really, really ugly. Let me see whether I can find this back for you, because this is the part we skipped, but it gives you an idea. Okay. So this really was the problem. So, you know, we need intermediate representation. So we can optimize without looking at the source code. So we can support new features without changing the backend to the I mean, there are many good reasons to do this. And when you do direct to C, it just doesn't work. But this is an effort we put in like a couple of years ago. So I didn't have time to say I'm going to rewrite the compiler from scratch. So I needed something incremental in order to do this. And what we did was to say, well, we are going to design what we call decode. And it's a D, not because essentially in our place where we write it with $. And they are extremely elementary expressions and statements. They are homogeneous and they have a very simplistic semantics. And what we do is that we look at the syntax and we transform, we lower the YAFL statements and expressions into decode. So and it's intrinsically incremental because the things that we do not recognize, we leave them as they are. But the ability to have a lower level representation means that at the end of the day, when it comes to compiling, we need to support those low level and not the variations on how they are expressed in terms of the source code. More specifically, we even went as far as supporting a concrete syntax. Because decode is a way, what I mean concrete syntax is that we can actually write decode directly in YAFL code. It's not meant to be. That's not the way it's meant to be used, but it can be used this way. And the original way is for the compiler to replace high-level statements into decode before proceeding. And for instance, and the syntax is awful. It's made with those little carrots, as you can see here. And the first statement in the log says call methods from the stream module, the output stream class, the write line method, and you apply it to an object which is the read once object, which goes standard out from streams, and you pass it on. I mean, you can see that this is not meant to be read, right? This is not comfortable. This is not fun. But the whole idea, so this is not meant to be written this way at all, but high-level YAFL code gets translated in those low-level capabilities and then compile. So that, for instance, if I were to support lambda calculus, support lambdas in general, I could do this without having to support lambdas in the backend. I could do it entirely at the decode level, for instance.
So if I understand correctly, you compile all of YAFL to decode and then decode to C, right?
Yeah, but
Okay.
but all YAFL to decode is an n-to-1 relationship. There are multiple things we write in YAFL that go to the same decode. That's the whole point.
Yeah, it's like a canonical simplified representation.
And
yeah.
Interestingly enough, you have an explicit semantics. When you write J becomes 99, from a distance, you've been taught it's an assignment. And if you look at the assignment, you can say, well, the assignment is an assignment. And if you look at this from a decode perspective, you realize it can be, there is, in the concept of assignment, there is a binary assignment, y assigned to a local variable, and there's a ternary assignment, which assigning to an attribute of an object. And then you have to say which object it is. So all these things are made explicit in decode so that translation gets straightforward from there on.
And are there other examples of analysis that you would like to do? And I know maybe control flow or things like that.
There are some, but the benefits are minimal. There are things we can do to improve analysis and recognize, oh, here and here and here, for instance, I don't need to deal with the garbage collector, because that's where what I'm trying to say is that a significant part of the time is spent in managing the garbage collector, because say, oh, if I need to garbage collect here, sorry, if I need to garbage collect here, I need to make sure that all my data, all my information is up to date. So if I have a capability of saying, oh, between here and there, I can statically guarantee that there will be no dynamic allocation. And because there's no dynamic allocation, I'm not going to need more memory. If I'm not going to need more memory, there is not going to be any garbage collector needed anyway. I can then say between here and there, I can simplify my code accordingly. That's the kind of thing we could do. But there is no low-hanging fruit any longer, because 30 years have been spent on this.
Yeah, okay. I was curious about these intermediate presentations that you said you wanted to add. This decode, I would put it more with code generation. It is kind of part of that process, I would say.
Yeah, we can argue about that. It's because if you look at this decode,
Yeah.
it is in ways it's not all that different from LLVM. I mean, it is not LLVM per se, but you will recognize stuff that are similar to LLVM there.
Yeah, but I bundle LLVM in code generation. Like.
Okay, then
it's just because it's something we don't talk about in the course. So I want to give students example of things that we might not see, and just for them to know that they exist.
But for instance, one of the hope I had, which I've never been able to materialize yet, is I don't have an example here. Let me get back to where we were. Is an example like the we're going to get there in a second. Yeah, and this is not a very efficient way of doing this. I would like the quantifiers can be really, I mean, if you look at all the combination of how things can be done, they are really complicated to generate. I would like to be able to express this as a combination of decode, and I'm not there yet, because there are things in quantifiers that I cannot express adequately in decode at this point. So I'm not, totally out of the woods, but I have good hope that eventually I'll be able to. If you look at the code that generates the thing for those quantifiers, that's really, really ugly, and that's one of the things I want to simplify. Do you feel like the bug from hell, or have you had enough? I have no ego. I'm perfectly okay with you saying, oh no, I have had enough. It's whatever you feel like.
Someone said sounds interesting and got some upvotes, and nobody posted a question.
Well, I have a question if you don't mind.
Sure.
First of all, thank you very much for your presentation. It was really interesting. Do you have any concrete example of projects where you use YAFL instead of developing Java, C, or C++ code? And do you have other projects where you prefer to use Java, C, or C++ instead of YAFL? And didn't you develop YAFL in the first place because you don't want to use other languages?
So, to be totally candid with you, I developed the YAFL because I was an too arrogant student. So I think you have to be honest, and I can rationalize Posthoc all I want. The truth is, there is no good reason. When we started having YAFL in the beginning, we did everything in YAFL, and there are things within YAFL we shouldn't have done. We did graphical user interface application with YAFL. It worked. We managed, but that was very inefficient. And that's why it's an area where we backtrack. Today, the rationale has gotten very simple. Either what we do is very, very, very limited in scope and needs determinism in memory. You know, I can't get into the details, but sometimes we have to write things that are literally either real-time or like real-time, and those we write in C. But that's A, it's minor, and B, it's always very small. It's always very, very small. That's a matter of principle. Because, you know, so listen, if you cannot have a system with garbage collector based on running as a real-time system is just looking for trouble that we don't want. So that's one case. When we write things that are essentially compilers that have no interface with the external world. So essentially you read text and you produce either text or binary format. Sometimes we use YAFL because YAFL is our passport to eternity, if you see what I mean. If we do something that has to live forever, we will typically use YAFL. If we need to interact with an API, and in our case, it has happened quite a lot that it has to do with C#, with .NET, then we write it in C#. Because when we write something in C#, C# is an adequate language, but the main concern I see with C# is that it requires me to have a .NET environment. But if I have to interface with .NET, that is not an additional requirement. It just comes with the package, so that's fine. That's pretty much how we would split things. But with YAFL, the scope of what we do with YAFL has restricted. It's only single-threaded. We don't start multi-threaded system with YAFL. We have support with multi-threading, but it's not as sophisticated as it should be, and that's not what we try to do. So it has to be single-threaded. It must be batch, so there has been no user interface, and no interface with existing APIs. And if those three conditions are satisfied, then YAFL is the greatest tool we have.
And aren't clients reluctant to use your service because you are the only ones using YAFL? And
oh, yeah.
So if for X or Y reasons you go bankrupt in 10 or 20 years, your clients wouldn't be able to translate their products or their codes into another language.
Okay, the case you make has been tried a number of cases. In practice, what we do is unique. In practice, what we do is, I mean, people don't come to us. I mean, we sell to literally the entire planet. They don't buy from us because we fund. They buy from us because what we do, they cannot buy elsewhere. So they're not abnormally picky. And people do not buy our services per se. They buy our products. How they're done is to a vast degree our problem. That's the first starting point. The second point, but that doesn't mean I don't have uncomfortable conversation. Say, oh, what are the system written in? And say, okay, well, this is going to be fun. It's an internal language called YAFL, and usually people say, okay, whatever, and they move on because, you know, what can they do? In practical terms, let's say we go bankrupt in 10 or 20 years, which is, you know, if you think of it, it's fantastic. What I mean by fantastic is 10 or 20 years guaranteed survival nowadays is really great. I could really live with that. But if we go bankrupt in 20 years, the YAFL compiler is there. We have a bunch of engineers who know how to do this. And we tell people, if we go bankrupt, you know who to hire. You can hire our people to start working on this. On the other end of the spectrum, what we write is very, very, very specialized. You know Java, you know C#. If we wrote our kind of compiler with C#, trust me, knowing C# won't help. It's not enough. In other words, just the fact that it's written in a mainstream language is only a very, very small part of the problem. What you need is expertise. And to push the question even further, YAFL as a language is very straightforward. Anyone who comes to us and says, oh, you know, YAFL is too hard for me, I need to take time, say, hey, I mean, anyone who knows IT and wants to write compilers should be able to read and write YAFL code almost out of the box. In other words, yeah, it's a conversation we have, but it hasn't been that much of a concern, the truth is.
If you were to start again, say you restart the company somehow, go back in the past, restart the company, but you didn't do your PhD and you didn't have YAFL, would you think it would make sense to take the time to write YAFL from scratch with the business in mind?
No, no, of course not. As I said, I tried to make it honest. Part of what happened, so it would make sense, but there is no way I would have had the wisdom to do it.
Yeah.
In other words, I'd love to say, yeah, it was a clear vision and I knew exactly what I was doing. And that's rubbish. That's rubbish. I was as clueless as it gets.
I think it would take a lot of confidence and you would have so much pushback that.
Oh, trust me, confidence I always had and pushback I got as well, as much as you can have. It's it's an interesting question, but it's very speculative.
Of course.
But and that's why I tried to make the case. Say, listen, it happened. It worked out really fine. It really worked out fine with us. But obviously, many of things were just happened by chance. Many of these were just chance encounters and mere luck that turned out the right way. And then, I mean, there is a very good business rationale for this, but I mean, I wouldn't dare go to a 25 years old and say you have to write your own language because, I mean, that sounds like, wow, that sounds like a very crazy advice. Do you want to see the bug from hell?
I'm interested at least. And well, normally it's a lunch break, so if you guys have to go eat, you're free to go. But I see there are some people that are interested by the bug anyhow.
Yeah, the bug from hell is really the bug from hell, right? It's like wow, look at this. So we've got a garbage collector. The garbage collector frees objects that are no longer accessible. A garbage collector can have imprecision so that it does not instantly deallocate something while it could, but that's probably okay. But the worst is for a garbage collector to deallocate something it shouldn't. That's like the absolute evil. That's what you try to avoid. And the real problem, it happened from time to time, like literally once a year. That gives you an idea of how bad it was. It happened once a year. It was extremely, extremely hard to reproduce. And we looked at it, and there was no way we could deal with it other than brute force. What I mean by brute force is that year after year, we had more powerful machine. And at some point, one of my colleagues said, okay, do you know what? This bug is too annoying. I want to deal with it. I want to deal with it in a serious way. And what he did is essentially calling the garbage collector between each instruction. As you can imagine, it took like weeks, literally weeks of CPU to actually go there. But this is how he has been able to reproduce the problem and say, okay, oh, now I see, here it's fine. I do this, and now my garbage collector collapses because it has deallocated something it shouldn't have. So this is how we did it. So it's brute force. There is no intelligence. There is no insight. It's brute force. And what does it look like? So this is a way of expressing something that the YAFL compiler could do. Say I have a function that receives 3 parameters, and the caller has to store in some kind of table for the garbage collector a reference to the 3 variables. And you have something that could look more or less like this. If you know C, this looks probably understandable, where you say, okay, I've got a P pointer, which is my pointer to my garbage collection table. I'm going to store a reference to, I'm going to store V, and I'm going to increment, and then store W, and then increment, and then store U, and then increment. If you look at this, the equivalent is this, right? So What's wrong? Who knows C well enough to say, oh, but this is not correct. This may not be correct, to be more to the point.
Does it have something to do with implementation defined behavior?
Yes, but where?
If I had to just give my first thought, it would be like the ordering of instructions, like compiler is free to reorder some stuff.
Yeah, but not all. That's the real issue is that if you execute, say, the middle assignment, you still, before the first, you're still good. The problem, it has to do with ordering, it has to do with compiler related stuff, and it's extremely subtle because in fact, the C standard tells you that these 3 instructions are each going to be happening before the matching assignment. Sorry, they're going to happen after the matching assignment. But then they don't guarantee that they will happen right after the matching assignment.
Mm.
And in fact, this is an equally valid ordering. A C compiler can decide, for reasons that doesn't have to justify to anyone, to generate the code on the right rather than the code on the left. But if you do the code on the right, you will realize that you, instead of storing V, W, and U in your table, you are going to store V and override V by W and override W by U. So V and W will not be stored. I told you it was annoying, but it's called the bug from hell for a reason. And the real problem with this, why is it so hard to reproduce? It's because garbage collectors are really robust, are really redundant beasts. If I have an object and say that I have 4 references to my object, and say for the sake of the argument that one of the references is lost, doesn't matter because the garbage collector will still not deallocate the object because I have the 3 others. So for the problem to be shown, you need a very, very unique combination of events. You need to have 1 reference. The object cannot be referenced. There is just 1 reference to that object. And that reference happens to go wild. And just at the moment that reference goes wild, I'm starting a garbage collection. You see the conjunction, the 3 events are very improbable. And they have to happen, the 3 at the right time for the problem to appear. And then you deallocate the object and you shouldn't have, and then you die. So if you think of it in retrospect, if there are lessons to learn here, is that garbage collectors are conservative beasts. They are designed to be conservative. They are designed to be robust and redundant. They are designed to suffer possible flaws quite gracefully. But on the downside, because they're robust and redundant, they're extremely, extremely hard to stress test. And they're extremely hard to get right because, as I say, they survive most of their own bugs. If you have something which is fragile, it crashes almost instantly if something goes wrong. That's annoying, but at least it's easy to reproduce. The problem with these bugs, with anything that has to do with the garbage collector, is that the situation has to be reproduced, and there are like literally an infinity of situations, and they will survive most of their own bugs. But if you bump into the one that is not, then you are in big trouble because it's going to be very hard to reproduce. Voila, that was the bug from hell. We are a little bit over time, but let's say just 5 minutes, so I think it's kind of okay-ish, I'd say.
Yeah, it's okay with me.
Voila, that was it for me today.
All right. Darius.
Yes.
Yeah, so we'll leave you the chance to ask a last question. And Darius, do you have time to chat afterwards, maybe on Zoom?
Sure. It's not as if I'm going any places.
Okay, great. Any last questions, guys? Now's your chance.
Okay. don't let me be the last thing standing between lunch and you guys. So thank you so much for taking the time.
Wait, someone posted a question.
Okay.
Ryan asked, besides YAFL, what are the languages that you find the most useful today?
Oh, gee.
That's a tricky one.
That really is a tricky one. Do you know what? I cannot answer because I'm spoiled. Try to imagine that you can, whenever something annoys you in the language you use, you can choose it. You can change it. You can make it exactly the way you want it to be for you. That's my position. In other words, it's like whenever I use another language, I can. I manage, but I feel constrained because I'm following someone else's ideas. When I use YAFL, the language is made for me, and that's part of my gratefulness to my colleagues because they accept things that they may not agree with. But because I can do C. I enjoy doing C because it's fun, even it's very different. I do C#, and I think it's not that much C#, but the development environments around C# are really amazing. I hate C++. I hate JavaScript. I'm not smart enough to do Haskell. That's designed for people much smarter than I am. I can do SQL. Sometimes SQL can be a lot of fun too. Voila. But yeah, for me, I'm not saying it's the best language, don't get me wrong. It's the language I'm the most comfortable with because, I designed it that way. I designed it to be the most comfortable for me. But I appreciate that it may not, feel the same for other people.
Oh, and important question. Is YAFL available somewhere, like if students want to play with it? Or is it like a well-kept secret?
No, if you want it, we'll be happy to share. It's not available somewhere because, but if you ask, we'll be happy to provide you with a working environment to play with it. But to a vast degree, it's underwhelming. It's just yet another language, it's so the entire story here was not that much about saying, look how great YAFL is. It was about, look at what the challenges and the benefits are of deciding to build your own piece of infrastructure for that. But don't get me wrong, anyone wants YAFL, please reach out and I'll be happy to provide you with it.
Right. All right. Thank you very much, Darius. And thank you everyone for attending.
Thank you so much.
Thank you.
And see you guys next time.
So on Zoom then.
Yeah, on Zoom.
Okay. Thank you.
Thank you.